everybody. Thanks for tuning in to our latest webinar. Uh, for those of you who've been here before, this is a familiar face that you've seen on many of our webinars. For those who it's their first time, we thank you and introduce you to Mr. Dave Giles, who is a member of our education team. And usually you know him as our EV expert, but guess what? He knows all kinds of information about ICE and hybrids. And today he's going to kind of talk about how those two things blend together. The chat is open for questions. And also, just so you know, at the very end, once this is done, we will email everybody a PDF version of the PowerPoint that you're seeing here in front of you. So just stay patient. But if you have a question anytime, just go ahead and put it in chat. Go ahead and take it away, Dave.
Thank you, Jimmy, and thank you for everyone for attending today. What we're going to be doing is we're going to be covering hybrid systems. This is a part one. There's about 4 parts to this whole presentation course, I guess you could say. And I'm going to start off with combustion engines and hybrids, talk a little bit about the differences in the technology, the strategies they use. Some of them may surprise you, and in how they work and what they do. Just as a quick brief overview, like Jimmy said, I work with the education team. You may have heard me on some FMIS trainings that I may have done with some of you out there. I focus specifically more so on the alternative fuel side, being that on electric vehicles and hydrogen drive systems, as well as I have vast background in the other aspects of the motive power trade, including diesel. So anyways, but I want to get started here. I don't want to kill too much time at the beginning going through the introduction, but I wanted to dive right into what we're going to be doing today. And if my little computer will cooperate. So the objectives of today is really looking at the different types of hybrid powertrains, the engines. I'm going to start with some of the earlier stuff. It may be stuff that you already have in your classroom, you might have available to you, you may have been donated, but I'm going to take it from not from the very first generation of the 2 most popular back then, which was the Toyota Prius and the Honda IMA, which is the IV tech engines, but we're going to push it up a little bit. So I'm going to be more into the stage 3 IV tech, as well as about the 2008, 2009 Toyota Prius. That's where we're going to start it. And then, of course, as we move through into our next webinar, we start talking the power split devices, how they're connected to the powertrain, and what they actually do in functionality. But let's get started with this area today. So what we want to do is we want to identify the main types of hybrid powertrains and their operating principles. Very important. You may hear terms like Atkinson cycle engine, auto cycle engine. We all know what auto cycle engine is, but the Atkinson is kind of a unique term that some manufacturers throw around, like Honda Dreams engines, and we hear about it in the IMAs, and as well as extensively through Toyota's lineup of their engines. Even in non-hybrid vehicles, you may hear about the Atkinson cycle engine, about efficiency and fuel economy and so on. So we're going to take a look at that. We're going to look at how those systems work, what they do, and how they actually operate within a conventional powertrain. We're also going to look at how a hybrid system integrate with that internal combustion engine, because they don't integrate as what some people may think. You know, some of these engines are directly connected to the drive electric motor. There is nothing in between. You know, some of them may have a slip plate, looks like a bit of a clutch. Others may not. So depending on the application, the 2 we're going to be looking at do have some sort of dampener in between. So, but once again, very unique setup by both these manufacturers and these early hybrid systems. We're going to look real quick at what is a parallel series, as well as a power split hybrid architecture, which is basically a series parallel hybrid that we see what makes up most full hybrids today. We're also going to look at the unique mechanical and electrical designs of the hybrid Toyota hybrid Synergy Drive, the HSD, as well as the Honda IMA. So that's kind of our objectives today. Very high level, not going to get a lot of in depth, but what I want to do is really make sure that I don't know how Megan does it, but she may just send the copy of this presentation to you right after we're finished. But be aware there is links in the presentation. There's also some animations. And so once again, the links themselves will take you to the reference videos or sources I have used when we put this presentation together. So then you could show the whole video right in your classroom through YouTube. I'm not going to go and show you the videos and show how it works and so on, but I definitely give you the link so this way you can access those videos that we're using to show your class. And it's really cool, some of the stuff that that's on here. So I'm just going to try and get this. My little mouse isn't doing anything here. So what is a hybrid? Basically, it's using two different power technologies that supplement each other, but can work independently. So, and that's why I went a little later with the Honda IMA, because the earlier Honda IMAs, like in the Insight and that, were real early design. They were essentially a 10 horsepower electric motor. It was a really 3-cylinder gasoline engine. It was a 2-stage IV tech engine. It was very early stuff. So we're moving a little bit further on where we're going to get into the 3-stage IV tech, as well as we're going to look at how even in a parallel hybrid, we can still drive the wheels of the vehicle, even though the electric motor is strapped and bolted directly to the crankshaft of that gasoline engine. So, which is unique in how they do it and the strategies they use within the valve train and the engine itself to make that actually happen. But we can see a series hybrid where essentially the electric or the gas engine doesn't drive the vehicle directly. The gasoline engine basically starts a generator. Generator powers a battery. Battery sends power to an inverter. Inverter to the motor. Motor to the wheels. That's a series hybrid, one path. We have our parallel hybrid that will share gasoline engine with the electric powertrain, but in most cases, the problem with the parallel hybrid over a series parallel hybrid is that parallel hybrid can't charge its battery while powering the vehicle, which is a unique aspect of a parallel hybrid over a series parallel hybrid. So a series parallel hybrid can use differing technologies with the engine electric motor. It can switch back, drive the vehicle electrically, use the gasoline engine to charge the battery, hence the Prius going backwards. Runs the gas engine to turn MG1 to powers the MG2 to run the engine backwards. So because obviously in a Prius, which we're going to be looking at, it has a power split device and there really is no reverse. So essentially a planetary gear set that utilizes the motors to give direction of power. So, and we'll look at that in one of our other sessions, the difference between how some of these manufacturers are putting power to the output drive wheels in different applications. So the two main ones we're going to be looking at today is obviously the parallel system in Toyota or in a Honda, which is our IMA. And now the early IMAs were actually rated as a mild hybrid. And back in those days with the early Insight, they really couldn't drive their own wheels with the electric motor. The motor was really a supplement to the engine. It helped start the engine in some cases. But if you looked at some of these early Honda hybrids as well, they actually had still an electric starter motor, a conventional 12-volt starter motor that didn't work unless there was an emergency and there was a procedure to shut down the high voltage system, which would revert to allow the car to start by the 12-volt starting motor. But otherwise, it would be started by the high voltage 120 about volt nickel metal hydride battery. So saying that, we have a parallel hybrid system, and then we have our series parallel hybrid, which is obviously our Toyota that we're going to be talking about today. So the hybrid series, full parallel, which we call a full hybrid, is a very complex way of strategies within the control side. What makes the series or the series parallel hybrid work is essentially the power split device. And in this diagram here, from one of our cutaways, we can see that we have the dampener inside here. We have this dampener. I don't know if you see my mouse there, but we have a dampener there. And then we also have our MG1, and we have an MG1, and then we have our MG2. So the MG1 and MG2 are unique to this series parallel hybrid. This engine uses two electric motors. Now, some people think that, once again, that the two motors work in conjunction with each other to directly drive the wheels. And in fact, the MG1 is a smaller electric motor. And the MG1's design is to help start the engine as well as provide charging to the nickel metal hydride battery, but also act as a CVT to the engine as well, or to the transmission output final drive. So it works in conjunction with the power split device in the sense of creating a CVT transmission by working with the MG2 on final drive. Unique thing about the MG2, which is a lot larger electric motor, it basically drives the wheels at the end of the day. So it's directly linked to the final drive of the vehicle. So as long as the wheels are moving, that MG2 is moving. Doesn't mean it's being powered, but it's also turning. So regardless of the wheels connected or not connected, through powering the three-phase motor, the stator in that MG2, it's turning. So anytime you're turning those wheels, essentially the MG2 is turning. So at the same time. So once again, there is some cautionary things that you have to be aware of hybrids and pushing them, as well as any electric vehicle too. So always refer back to the manufacturers in doing so, or else you could be putting 20 or 30 kilowatts of energy back into the system, because these are permanent magnet electric motors. They run a neodymium or a rare earth magnet style motor in these Toyota early powertrain hybrids. This is an example here. Once again, we can see the chain drive in this this hybrid. We call this a CVT, but it's actually ECVT. And we see the chain there. And I'm not going to get too far into this because I want to get back into the engine side, but we do see that there is the MG1 here. We call it generator. They're called MGs, motor generator. And then we have also our MG2 there, which I was just talking about in that sense. And then, of course, we have our power split device down here that helps transfer that energy, whether it's going to be gasoline powered through the MG2 or MG2 with gasoline power, or going from MG1 to charge the battery, or work with the CVT side of the vehicle by the power split device. It doesn't have a conventional CVT transmission. It doesn't have a varying, cone or any kind of belt drive that varies. That is all done by the electric motors. So, and this is one of our trainers that we do use to demonstrate that procedure. And this is one that can actually show the use of MG1, MG2, and so on to do that. Okay, basically Honda's parallel hybrid system is, we can see here, I got a bigger picture in a second. In a parallel hybrid, both the gasoline engine and electric motor are mechanically connected to the same drivetrain. So these are strapped together. So that means that this electric motor and the rotor inside that motor are actually bolted right to the crankshaft. Whenever that electric motor is turning, the crankshaft is turning. This is really important with these IMA engines. And as well as if the crankshaft is turning, the electric motor is turning. So regardless if the vehicle is being propelled, the electric motor and the gasoline engine work together. That crankshaft is always turning all the time. And in these later IMA engines, you can actually drive them in full electric. They will go low speed electric, not very far. They don't have very big batteries with the nickel metal hydride batteries, but once again, they don't go very far. but they can run full electric but the crankshaft is turning, the engine is turning in this thing. And some people say, well, that doesn't make sense because I'll have pumping loss within the combustion of that engine. And Honda does some really cool stuff with that to be able to reduce that. Now, looking at the IMA engine, beyond, its lean burn combustion, its high efficiency, lightweight design, the engine's actually a thinner design. A hybrid engine is essentially a little lighter than a typical combustion engine from a non-hybrid vehicle. So we see a lot more efficiency out of these engines. But one thing about Honda compared to Toyota is that Honda really focuses on engine design. They believe that a lot of the efficiency, the range, and performance comes from the engine. And Toyota's the opposite. Actually, Toyota relies more on the electric motors, where the gasoline engine supplements those motors, where in Honda is the electric motor supplements the gas engine. So a very unique process with these guys here. We do see a belt here, conventional CVT style belt within this transmission. In fact, some of these early Hondas, you could have got them with a 5-speed manual transmission with a hybrid design. So once again, single motor, but unique design within the engine itself. The engine itself has the iVTEC Stage 3 motor, which is very unique to the hybrid Honda lineup, and we'll see how that works in a second. So once again, we just talked about this. Honda is using engine efficiency and strategies by electric motor relies on the engine. So the electric motor needs the gasoline engine to really make it work well. Toyota, opposite. Toyota relies on the electric motor. So the electric motor becomes more dominant in the Toyota, where the gasoline engine is essentially assisting that electric motor. So very differing technologies between the two competing manufacturers in these early hybrids. So the IMA 3-stage iVTEC engines has three, and the 3-stage is basically the 3-valve operation. So they can do different valve arrangements and their opening based on what they're actually doing. So we have our low speed operation. And now mind you, I do have, these are screenshots from a video from Honda. I could have put the video in here, but I thought it'd be too much and it'd be too long. So I put the link for all this stuff within in this presentation. So this way you can review it, show it in the classroom. It's really good because you get a lot of students that are Honda, they have Hondas, they have Civics, and when they see what actually happens within some of these iVTEC engines, especially with the 3-stage, it's they're pretty surprised. And it's a great way to question students as well. So in this case here, we have low speed valve operation, once again, enabling, limited amount of air fuel going into the cylinders, filling that cylinder, high-speed valve operation. Once again, adjusting the lift within the valve train to maximize efficiency, but also performance as well. And then we have what we call valves deactivated, and this is the unique thing with the IMA engines is this valve deactivation. It actually shuts the valves off, and not in the way you think. It's not turning them off and just stopping ignition and fuel. It actually closes the valves. And let me just back up a little bit here. Rather than just shutting the valves, the engine's management system is so in tune with its fuel delivery and its operation. What it does is as the piston travels up to top dead center after doing the power stroke and is pushing out the exhaust, when it pushes out that exhaust, it closes the exhaust valve and seals the cylinder. It happens in milliseconds based on engine RPM, of course. And then what happens when the piston goes down, the intake valve stays closed. That means there's no air or fuel being drawn into that cylinder. That means there is no pumping loss within that engine. So what's happening now, there's no resistance. So it's really a hard concept because you think, Well, there's nothing there. There's nothing to pump. So there's nothing in the cylinder. And if there is anything in the cylinder, the space within the combustion area will take up that little bit of air that may have been trapped or left over within that cylinder. So the engine actually kind of spins freely as if there was no head on that engine. This allows the engine to run in different modes. So allowing the electric motor to actually work like an electric motor, making this vehicle a parallel hybrid. Early IMA engines could not do this. They could not run in this mode. But in the later ones, Honda came up with strategy, once again, going to their engine technology. And, once again, Honda is famous for its VTEC engines. And it's all about the valve train and the valve arrangements and how it works within the VTEC engine. And we see valves deactivation in this mode. So let's take a look here. When you're in electric motor only, question is, in drive electric mode, are the valves fully opened or fully closed? And it's a great question to ask the students, because that will give them insight into what's actually happening inside a combustion chamber. So the engine, basically, when I go into electric mode only, let's say I'm driving through a parking lot, the engine reverts to electric drive based on the battery voltage and speed and throttle input and lots of variables there. And then basically it deactivates those cylinders. And by deactivating those cylinders, there's no pumping loss. So that means that it can travel a little bit further. If it didn't do that, let's say the valve was able to open and suck in an air-fuel charge, close the intake valve, compress it, that compression would cause resistance on the electric motor, which obviously would reduce the distance that engine can travel. So I actually asked the question, when else does this condition, do you think, can occur? And this isn't just in electric mode only at low speeds. It can also happen at low speed cruising. You could be doing 40, 50 kilometers an hour. You release your foot off the accelerator. The gasoline engine deactivates at that point because it knows the electric motor can manage that speed or that distance, however far you're going. And basically it can allow the engine to run electric, even not at a low speed. So it's low speed cruising, but once again, cylinder deactivation is a prime point when it can happen with low speed cruising on this engine. Now, regeneration, same thing. When I'm coming to a stop and I'm hitting my foot on the brake, same idea. I want to capture the energy from the wheels of the vehicle and not from the engine itself. So once again, it goes into cylinder deactivation, seals the valves, cylinder has no pumping loss, and it's gathering the energy directly from the wheels, maximizing the amount of resistance through regen from the electric motor's EMF, essentially being captured back and charging the battery. So unique sides of it, very important part of this IVTEC system. Once again, managing that system, make sure the oil's clean, and these valves and how they operate are very similar to modern IVTEC engines as well. And but the thing is once again a very, very broad point of this efficiency within this engine. So once again, this came from Honda's three-stage IVTEC link. So you can have the link there from YouTube, and it's a great way of doing it. Now let's move into the next guy. The Toyota's approach to engine technology, very different. Once again, we have the Otto cycle engine, and then also we have this Atkinson cycle engine. And you'll hear a lot of times where Toyota will have an ad on the Tundra. I think I have a picture of one here where they say, Tundra's new V6 engine, Atkinson cycle engine. And it's like, well, sounds pretty good. I have no idea what the Atkinson cycle engine is. And if somebody looks it up, they probably go, oh, dear God, it's not it. I don't know if this is what's in my truck or not, or what I'm going to buy. But let's take a look here. First of all, all hybrid engines in Toyotas use an Atkinson cycle style engine. So they all use the Atkinson cycle. But in non-hybrid conventional combustion vehicles, they can also run the Atkinson cycle as well as they can run the Otto cycle engine. So, for example, you may see ads out there advertising the Atkinson cycle. What is? Otto cycle engines about power, four strokes, we conventional engine, basically our four-stroke engine. Atkinson cycle, a little different. They change it up. Problem with Atkinson cycle engines, they're not very powerful. They're not a powerful engine. That's okay in Toyotas, regardless, because in a hybrid running an Atkinson, we have the electric motors. And that's why Toyota dominates on the electric motor side, where the gasoline engine supplements the electric motor, like I mentioned earlier, where Honda is the other way. Non-hybrid vehicles will run an Otto and Atkinson cycle engine. They run the best of both worlds. They can do that. So, meaning when they're under power, they can run the Otto cycle, and then they can switch the valve. Once again, talking about how they're doing it by the valve train, and they basically can go into an Atkinson cycle. Atkinson cycle is very unique as well in how it works and what the valve train actually does. Low speed cruising. Now, just back up a little bit, we do find Atkinson cycle style engines in other manufacturers as well. Low speed power. Once again, with Atkinson cycle, I don't get the power. I don't get the efficiency. In fact, an Atkinson cycle engine can only spin at about 5,000 RPMs. So obviously we know that these Toyota engines and our Tundras and stuff like that can spin way faster. And that's when the Otto cycle will kick in, to maximize power and stuff like that. So the Atkinson cycle essentially, unlike the Otto cycle that fills the combustion chamber as much as it can, it pushes up on the piston, creates the power, piston goes down and rotates the crankshaft. Pretty straightforward. What goes up comes down in that it's the same stroke going up, same stroke going down. Atkinson cycle engine mechanically does the same thing. The crankshaft, the piston still goes up, still comes down. The difference is how much air fuel is in that cylinder. So in an Atkinson cycle engine, what they'll do is they'll actually open the valve, on the intake, and as it draws it in, it sucks in the big charge. But as the piston goes back up, it actually hangs that valve open, essentially pushing some of that air fuel back into the intake, but that's okay. It can get it from the next cycle. And as it gets closer to the top, the valve closes. And then, of course, there's not as much combustion. So what Atkinson cycle is actually a shorter intake stroke with a longer, power stroke. So it's kind of, it doesn't have as much power because it's not filling that cylinder. So it's a shorter intake with a longer, basically expansion stroke. So it's kind of a unique side, but runs the same engine. If you take both engines apart, they look the exact same. Advantages and disadvantages on this style engine: they require less mechanical stress, which can reduce reliability. The efficiency is way higher on an Atkinson cycle engine. Toyota claims 12 to 14% efficiency. These engines are lighter, just like Honda. They're a lighter design, thinner walled engine. Once again, and fuel consumption is reduced because, once again, I'm scavenging from the intake. I'm running a shorter compression stroke, filling the cylinder less, but the crankshaft still has to go on that expansion stroke, still has to turn, but just doesn't have as much power. Once again, that's the biggest thing, is the less power in the Atkinson cycle. Hybrids don't have to worry about it. The MG2 will take care of that. It will give the extra power it needs to supplement the lower output of, I believe the Prius is around 78 or 79 horsepower on this gas engine. They have a lower maximum rev limit, usually around 5,000 RPMs, given their timing settings, because once again, the expansion stroke has less power, so at a certain point just runs out of that energy to turn the crankshaft. And once again, the Atkinson cycle needs a more complex technology in of its valves and camshaft, but also in its strategies and its electronics. So, oops, I lost my, I apologize there. I thought I had my, oh, here it is. Here, I don't know why it didn't show. So to give an example here, if we went to a conventional Otto cycle engine, this is what your typical Otto cycle engine is. And this is in the presentation. I don't know why it didn't come up there. And if we look at the Atkinson cycle engine, there's actually 4 different designs of the Atkinson cycle, but this is an Atkinson cycle. So when somebody first talks about what is an Atkinson cycle, and you basically type it in and you get this and you go, there's no way they're using that in my 2025 Toyota Tundra or in my 2025 Prius Prime. But this is the Atkinson cycle. And what you can see here is you can see the shorter intake stroke for compression, but the length of the expansion stroke is still very long. So it's utilizing efficiency. It's utilizing basically less wear and tear because doesn't have to compress the same compression as in the Otto cycle. So that's a real quick high level overview of this early technology. I just want to get us warmed up into what they're doing within these engines, especially some of that terminology can be very misleading to students, could be confusing in the sense, but once again, understanding the basic fundamentals and principles of what these two cycles are, the 2 different technologies are, and how manufacturers with their engineering has modified these systems to do what this Atkinson and system is designed for, and do it in a way that they can still utilize a conventional engine, but make it work like an Atkinson engine itself. Okay, so anyways, that's the end. And if anybody has any questions.
So far, there are no questions in the chat. That doesn't mean there won't be some. You did good, too. You were only 2 minutes over, so.
I know I did good. Isn't it great?
You did really good.
That's because I didn't babble at the beginning.
So Dave pointed out this is part 1 of 4?
Yeah, 4. We're going to be doing another couple more so on the hybrid. We're going to do power split device. We'll do like how it's coupled, how the CVT works within a hybrid system. Then we're going to look at the electric motors. We're going to do some testing. I'm hoping to have a couple live units here, which I'm prepping right now. So it's a multi-part system just to give more. It's a breakdown of our hybrid delivery system, moving right into modern engines as well.
So everybody will get a copy of the PDF, and like you said, there are hot links in that PDF. Oh, yep. We do have a question. When Honda closes all the valves, that does not create any kind of resistance?
No, I know. It's like, no, it doesn't. Other than a little bit that's in there, but it's a lot less than if it had filled the cylinder normally and compressed that combustion. And that's why I put the link there, and it's right from Honda. It's a great conversation piece to have with students. Show the video. It's about 4 or 5 minutes long. It explains how it works. It's really great, and it's great for discussion because it's what we think is really not what we that we might think that the engines actually do. So so it's a great discussion. So yes, it reduces that resistance very, very greatly to reduce that pumping loss from the engine itself.
So it says because there's very little air inside the cylinder, is that correct?
Yeah, so as it exhausts. In fact, and I haven't proven this out. Actually, somebody said when it exhausts the last time, when the piston's going down, the intake valve's closed, it actually fires the spark plug one more time, as the piston's supposed to be going down, pulling on an intake charge, but the valve is closed and is really trying to burn whatever's left in that cylinder. This way, when the piston comes back up, there is nothing in the cylinder. There's like really, if anything, it's inert gas in the cylinder, which is, at that point, not compressible. So.
Excellent. So that hot link will be on the PDF you receive.
Yes.
You will also receive a recording of this. Anybody who signed up, you'll receive a recording as well. You can rewatch it, play for students. Maybe we got you on the line, hooked in. It's part 1 of 4. So we'll send you out communications when the other ones will occur. And of course, check our social medias. Other of our webinars are all up on our YouTube page, which I encourage everybody to like, subscribe. We have a lot of followers. We have a lot of great information on there. It's not just about the products we manufacture, but about educating you, the educators. So I don't think there's any more questions, Dave. So
Okay,
unless
great.
you got anything else to say, we can wrap this one.
Okay, well, everyone, thank you for attending and have a fantastic super day.
Thanks for your time, Dave.
Thank you. Thank you, everyone.